Hi guys, thank you all for coming. This is our number 4th in our community education series. Today Amanda Nascimento is here to do our genetic counseling education. This is super interesting and it's a service that we offer at our cancer center that a lot of people don't know about. So trying to get the word out on that, and I will let you take it away.
Thank you. So as Angie said, I'm the genetic counselor in the cancer center, and I'm also a health coach. So today we're going to be talking about cancer in sort of the relation to genetics and also lifestyle. So I also used to be a teacher, so I am going to be asking some questions. So if you're brave enough, chime in. With that said, we can't talk about cancer without talking about cells. So who might be brave enough to share what you know about cells? What is a cell? I won't call on anyone, I promise. But
teachers call on
teachers call on people. I'm no longer a teacher, so okay, I won't put anyone on the spot. So cells do a lot of things, actually. So cells are building blocks. Cells give our body structure. So think of like bone cells, you know, in your skeleton, give your body structure. Cells give structure to our different organs, like our heart and our brain. Cells do, a lot of things for us. Cells convert nutrients into energy. Cells do a lot of things. While they may have different functions, like a brain cell is different from a liver cell, is different from a bone cell. Some similarities between cells and what we want them all to do is to grow, is to function in whatever capacity they're supposed to. So we want bone cells to be bone cells. We want them to divide, and that means to make new cells. So we want bone cells to make new bone cells. And we want them to die when it's appropriate. And so, I'll just advance because we're going to talk about cell death in a minute. So you don't have to take in this whole animal cell structure. What I want to show you, though, is really how complex a cell is, right? We have multiple trillions of them, and they're so small we can't even see them with our naked eye, and yet within this little teeny tiny structure are even smaller structures. So it's a really complex system. So we're not going to talk about all of it today, but we are going to focus on two things for the most part. So the genetic information, which is the DNA, the genes, the chromosomes, which are found in that center structure called the nucleus. So we're going to focus on that, and we're going to touch on the mitochondria, which do a lot of things for our body, but most famously, the mitochondria produce energy. So these are really important things. So we want, the DNA to function and be stable, and we want the mitochondria to produce energy. So I spoke about cells needing to die. So this is showing you a process that you don't have to remember the name of. It's called apoptosis. And this is a process of programmed cell destruction, which I know sounds really terrible, but in fact is actually really important. So pretend this is, say, a skin cell. So we have skin cells that, at the top is a healthy cell. You can see the chromosomes. And then maybe there's an injury to the cell. Maybe you get a sunburn, and then that cell gets some injury to the genetic material. So you can see some of the yellow sort of chromosomes. That's supposed to indicate injury. So cells actually have a way of repairing themselves. So cells have a DNA whose job it is to code for proteins that fix damage. So what we hope for is that damage is detected. It's, the little mechanics inside the cell are recruited, they fix the cell goes on to live its life. Sometimes the cell attempts to repair the damage, but the damage, maybe you get another sunburn and there's more damage to the DNA in your skin, and it just kind of overwhelms the cell's ability to repair itself. So then what happens in the good situation, the good scenario, is the cell detects that damage is just too overwhelming and it programs cell destruction. So this is a good thing, because when that doesn't happen and we have damaged cells making new damaged cells, making more and more and more damaged cells, we get something like cancer, right? So cancer has several hallmarks. This is not all of them, but when you think of cancer, we think of cells that don't have that programmed cell destruction, that apoptosis, can't do that anymore. So you have these cells that are damaged, that are dividing uncontrollably, making new cells. And then they're really the hallmark of cancer that makes it different from non-cancerous tumors is that cancer can spread. So, not the ideal situation, of course. So just an illustration of this. So on the left is a healthy cell that's dividing and making new healthy cells, and then you get some kind of tissue at the bottom. So maybe that's like, your skin, to further that example. On the right, we have a skin cell or whatever normal cell that transforms into a cancer cell, and then uncontrollably grows and grows and grows and grows and grows, and then disrupts the, say, skin, tissue or whatever. So you can see that on the bottom where tumors just take over and they disrupt the normal function. So in our skin example, that might be like a, skin cancer or something. People get that on their face or their arms or whatever. So the million-dollar question is, how does a healthy cell actually become a cancer cell? And so this is science, so nobody agrees, of course. It's controversial, and the jury is still out. Some school of thought is that it's the damage to the DNA that leads to cancer. And some other scientists think it's damage to the mitochondria, and that leads to cancer. So, really evidence is showing both are true, and that damage to the DNA affects the mitochondria, damage to the mitochondria affects the DNA. So, I think we let the scientists battle that one out, and we just remember that we need cells to be healthy, robust, functioning, making energy, making new healthy cells, and then dying when appropriate. Okay. So just a little review, since I'm throwing around the words DNA, genes, and chromosomes. DNA is a structure called a double helix. So basically it's a twisty ladder. And then the rungs of the ladder are the DNA, we call them bases. I kind of think of them as bits of the alphabet, because there's 4 letters that make up all the DNA codes. The letters are A, T, G, and C. It's okay if you don't remember that. But basically, you think of like our alphabet has 26 letters that makes all the words that we use. The DNA alphabet only has 4 letters, and yet it can make the 20 to 30,000 different genes that we have. So DNA is very small, A, T, G, and C. DNA in a certain code will make a certain gene. And then that genes come together and they crunch down and compress really tightly to make chromosomes. So we're not really going to touch on chromosomes so much today, but just so you sort of have the vocabulary. So DNA makes genes, genes come together to make chromosomes. But ultimately, what we want to really focus on is proteins. So DNA is a code for proteins, and proteins do a job. So we have all kinds of different proteins in the body, and some of them you might have heard of. So melanin is a protein that is the protein of pigmentation. So melanin might make your eyes blue or brown or green, your hair a certain color, your skin a certain color. So there's a gene through a DNA code that produces melanin that gives you pigment. Okay. There's a gene that codes for hemoglobin, which carries oxygen all around your body, right? So basically, genes are recipes for proteins that make us function properly. Has anyone heard of BRCA, BRCA? Yeah, some people? Okay. So BRCA1 and 2 are proteins whose job it is to repair DNA, okay, to repair the damage. So did everybody actually catch that? So the dreaded BRCA gene, right? Nobody wants the BRCA genes, right? But those are just 2 genes, BRCA1 and BRCA2. They code for the BRCA1 and 2 proteins. Those proteins stop cancer, right? By repairing damaged DNA. So the gene we often name genes after diseases, which makes them sound terrible, right? I mean, who really wants a gene named after breast cancer, right? Nobody, of course. But just to remember, the genes are just codes. The genes are neutral. They're not good, they're not bad, they're just codes. And they're codes for proteins that serve you, hopefully, serve you well. The problem is when there's a mutation in a gene, or I'm really supposed to say pathogenic variant, but if you don't tell anyone that I'm calling it a mutation, I won't tell anyone either. So we're just gonna call them mutations. So when there's a mutation in the DNA, right? So that means maybe part of that DNA is missing, maybe it's duplicated or rearranged in some way so that gene is not making the protein properly, or maybe not enough of it. And that's where we might see an increased risk for cancer. So poor little BRCA1 and BRCA2 are just genes that we've named after a disease. It's the mutation in the DNA code. That's what increases the chance of cancer. Okay, so your genes are not out to get you. Your genes are just code. So I like to think of the body as kind of like a symphony, right? We have all of these genes making proteins that all work together to help us function. So if we think of DNA, so the A, T, G, and C as musical notes, the genes are like the musical score, right? So a musical score is just a piece of music with the notes in a particular order, right? And the protein is what you hear. So what I want to do is play for you a little tiny snippet of the BRCA1 gene. And I'm going to play it through once without a mutation. And the second time I play it, and so what you're hearing is the protein. Okay? So the first time, mutations in the DNA code. And the second time, I'm going to insert a mutation. And I want you to listen for the difference in the protein. Okay? So I'm just going to sit down for that. So one little lesson is that all genes start with a start code. The gene has to know when to begin making a protein. So this is a start code for genes, A, T, and G. So this is, listen. Okay, that's start. And genes also need to know when to stop making a protein, because they can't just keep making the protein forever and ever and ever. The protein has to end. So there's a stop signal as well. And that stop signal, most of the time, is TAA. Okay, so start signal, stop signal. Okay, so listen, because I'm going to play the gene without a mutation again, and so listen for the protein. Okay, I have to cheat because I can't memorize the BRCA gene, so bear with me. So, okay, here's the start. Okay, did you hear that? That's the end, okay? So that would be just a really tiny snippet of the BRCA gene. It's a really long gene. We would be here the whole time just playing BRCA. Okay, so listen for the change in the protein. Okay, so here's the start. What do you notice about the second one? Much shorter, much shorter. Yeah, so what I did is I inserted a mutation in the code. So the top is the normal code. The bottom, you can see that red A was normally a G, but I inserted an A. And what that did was that coded for a stop signal. So that means the gene is going along, making its little protein, and then all of a sudden, boom, there's a stop. So you can imagine if that happens in a really important part of the protein or right at the beginning of a protein, it's not going to make enough, right? It's going to stop making that protein. And that's actually a fairly common mutation that we see in different genes is just within the gene, there's an accident, a mutation, and the gene stops making the protein. And there just isn't enough to do the job. And if the job is to control the growth of cancer, and there's lots of different ways DNA does that, then you can imagine there's a higher chance of cancer if it's a cancer-related gene. Okay. So about 5 to 10% of cancers, it depends on the type, but about 5 to 10% of cancers are due to mutations in these genes that get passed down through the generations. So in this case, the gene mutation is noted by that pink band. So dad is a carrier. So that's showing you 2 chromosomes. We have 2 copies of each gene and chromosome, right? Because we get one from our mom and one from our dad. So whether dad passes this down to a child is 50-50. It's a coin toss. So in this case, unfortunately, the child did get the gene mutation. So both dad and child have an increased chance of cancer. But that's kind of how it works. It's 50-50. And sometimes people don't inherit the cancer mutations, and sometimes they do. But the thing to remember is that even if you have a mutation in one of these cancer-related genes, it doesn't mean you're going to get cancer, right? It's rarely 100% risk. So this is where I think and we'll talk in a little bit, where lifestyle can come in and we can take a little bit of control of our cancer risk, okay? And you don't have to take in this whole graph, but what I wanted to show you is what the risks are for the high risk, famous, BRCA1, infamous, I guess, BRCA1 and 2 mutations. So just take that top line first. So in the general population of females, there's a 12% lifetime risk of developing breast cancer. Okay, it's just the background risk. For actually both BRCA1 and 2 mutation carriers, there's a range, but it's up to about 80%. So yes, that's a high risk, right? But these are the most, like I said, infamous sort of breast cancer genes. Oh my gosh, I'm going to get cancer. But there's a 20% or more chance that won't actually happen. So, just to put it in perspective, that it doesn't mean someone's going to get cancer just because they're a carrier of one of these mutations. The other reason I wanted to show this whole thing was to highlight that males do not get a free pass with BRCA, and I see it in the clinic all the time. Well, I don't have to worry about that because, whatever, I'm not going to get breast cancer. And it's not true. So you can see that the general population rate of male breast cancer is about 0.1%. So that's about 1 in 1,000. So if we think about Fenway Park holds maybe 38,000 people. So if there's a special night and only men are allowed in Fenway Park one night, just population statistics wise, about 38 men in that population, or males, will get breast cancer, right? So it's not zero. You look around at Fenway Park and you think, well, 38 men will someday get breast cancer. Now, if it's a very, very, very special night at Fenway and it's only males who are carriers of BRCA1 mutations, whole 38,000 people, they're all BRCA1 carriers, about 380 of them will develop breast cancer. Okay, so it's about a 1% chance. And then BRCA2 is actually higher risk. It's 7 to 8%. So we have, a stadium full of male BRCA2 mutation carriers, somewhere between about 2,600 and a little more than 3,000 of those men will develop breast cancer. So it's not a zero risk. Males don't get a free pass. And last time I checked, most males have a prostate, a pancreas, and skin. So this is not, a mutation or a gene that is irrelevant in the male population. Okay. So why have genetic testing? Why? The answer, as in most answers in anything related to medicine or genetics, is it depends. It depends. If someone is diagnosed with cancer, depending on the type of cancer, depending on the gene in question, knowing what mutation in what gene someone has can actually alter the treatment recommendation. So an oncologist could maybe suggest one medication versus another for cancer treatment. Again, depending on the type of cancer and depending on what gene mutation was detected. Also, surgeons can use that information to recommend certain surgeries. Again, depending on the gene, depending on the type of cancer. So there are actually treatment recommendations, or I should say, genetic testing can be relevant for treatment. If you don't have cancer, then obviously we're not thinking about treatment, but we're thinking about risk. So think about a jar that when it gets filled up with marbles, that's when we might have a diagnosis like cancer, okay? So all of us have marbles in our jar, we just do. Genetic testing can help you understand how full is my jar. Maybe I was born with, a certain, colon cancer risk because of a genetic mutation. And maybe my jar is already half full. Just as a little baby, I'm there and my jar is half full. So knowing that information can help you and your doctor make a plan, right? So if you're at risk for colon cancer, for example, you might have colonoscopies, not every 10 years, but maybe every 2 or 3, depending. Or, maybe if you have a particular mutation in a breast cancer related gene, you might have your yearly mammogram, and every 6 months, there might be a breast MRI. So MRI, mammogram every 6 months just to watch the tissue. Because, ideally we don't get cancer, right? But second best is we detect it early. So again, knowing how full your jar is can help you and your doctor make a plan to hopefully detect cancer early. Again, there may be other things, screening at a younger age from what would be normally recommended. And, maybe removing at-risk organs, something like an ovary. Obviously, that's going to depend on if a female has had children and she's done, then maybe, she would consider having the ovaries removed depending on the genetic test result. So, it depends, but it can help you make a plan. Genetic test results have implications for family members too. So a family member might decide to have testing or not, that's also the option, but they would at least be offered testing, which could lead to earlier screening, than would normally be recommended. In some of these genes, actually, if both parents are carriers and a baby gets 2 copies of a gene mutation, again, depending on the gene, that can actually lead to higher chances of childhood cancer, certain birth defects, and intellectual disabilities. So sometimes if a genetic result is relevant to a younger person who's still in that sort of childbearing years, if they're positive, that might spur their partner to be tested, because then there's things we're not going to get into today, but there's certain technologies that can be used to help them have a baby without 2 mutations. Sometimes genetic testing can be the motivator for habit change. If someone finds out that they have an increased risk, then they might say, okay, it is definitely time I get to the gym, or go swimming, or quit smoking, or whatever. Sometimes people just need a little bit of motivation. And sometimes it can give peace of mind, because sometimes test results are negative. Most of the time they're negative. But knowing that, you don't carry the same mutation that everybody in your family has can, make you feel a little bit more relaxed about your health. None of us has 0 risk of cancer, but knowing your risk is no higher than anybody else in the population can sometimes be, give you peace of mind. Can be nice. Insurance. Who loves insurance? We all need it, right? So whether or not insurance covers genetic testing depends. What health insurance companies use to decide whether someone is, let's be real. Whether it's worth them paying the cost of testing depends on certain factors. So it might depend on, have you had cancer? And if so, what type? And at what age? So we know when someone's a little bit younger and they're diagnosed with cancer, it's more likely to be an inherited form. So insurance always wants to know, what's the diagnosis? What's the age? Was there significant precancer, like a certain number of colon polyps? Do you have a particular ethnic background? For example, the Eastern European Jewish population is at a higher chance for certain genetic mutations in cancer-related genes. insurance will ask about family history. So anyone test positive for one of these genes? And that's pretty much the first question they ask all the time when I'm requesting authorization for testing. That's the first thing they want to know. And then they also want to know, okay, do any close blood relatives have cancer? Again, what type, what age? So these are all questions that insurance will ask. So to make that a little bit easier for you, if you're interested in thinking about your family history, your medical history, is I came up with a questionnaire that's right on that back table. And basically, if you check yes to any of those answers, I can never guarantee that genetic testing will be paid for, but you can certainly come to the Cancer Center and we talk about that. We can talk about your family history, your medical history, what you might want and get out of genetic testing. I'm happy to see you for genetic counseling. So that would just be a referral from your physician. So I tried to make the questionnaire super, super easy, but it's pretty comprehensive too. So like I said, I had been a teacher, so I'm giving you homework. Okay, so let's switch gears. We talked about genetics. Let's talk about lifestyle. So who, if anyone, feels comfortable chiming in? What are some lifestyle factors that might affect cancer risk, either positively or negatively?
Smoking.
Who said that?
Big time.
Yes, smoking for sure.
Sun exposure.
Say it again? Sun exposure, yes, exactly. Exercise, yep.
What you eat.
What you eat, yeah. Anybody else? Okay, you hit it. And you actually remembered the one that everybody forgets. So for those of you who actually can't see that, this just tickled me so much I had to include it. So it's a doctor talking to a patient who's like sprouting from every area of his body. And the doctor says, "I'm afraid you've been a couch potato far too long." So physical activity is so important, and not just for cancer, right? For really all aspects of our health. But yeah, so you hit on a lot of them. Smoking, 1 out of 3 cancer deaths is due to smoking. But the flip side of that is it's never too late to get benefits from quitting, right? So, you have a certain number of marbles in that jar. Smoking may, add more, but if you quit, you slowly start removing some of those marbles too, right? So it's never too late. Alcohol intake, I know we all hear different things like, oh, 1 glass of wine a day is good for you. And, who knows, right? But if you look at alcohol intake from the perspective of genes and DNA repair, alcohol does a lot of things, including preventing the absorption of some really important vitamins that are needed to repair DNA. So I will leave it up to you whether you, drink alcohol and to what extent, but it can decrease DNA repair. Physical activity, as we just said, is really important. Anything is better than nothing, and start where you are and go from there. Right? We all can improve, and that's the lovely, wonderful thing about the human body is it's really adaptable. So even if all you can do is walk to the mailbox and back, maybe next week you walk to the mailbox and a few feet, more. So just gradual, steady improvement. Stress management, can we say anything more about chronic stress? It's just terrible. But there are management techniques, and if you're like me, you're not going to sit and meditate, right? I cannot do that, but I find other things that I can do, and maybe you also can't sit still long enough to meditate, but maybe there's other things you can do as well. Sleep, sleep is critical. It's the foundation for all types of health, all aspects of health. And we all need a bedtime routine. Why is it only the little people get bedtime routines, right? Kids need a routine, so do adults. Community, and we're going to talk about community in a minute. Community, we're human animals and we're social creatures, right? We need each other. And cancer survivors who are not lonely survive longer than those who are. So somehow that connection is so critical to our health. So Lynn actually got the answer to this question. What have I left out? But the one thing that I haven't talked about is diet. Okay, and I know, we hear, 1 week eggs are like equivalent to smoking cigarettes, and the next week they're fine. And 1 week red meat is terrible for you, and the next week it has important vitamins. So, what is healthy anyway? And I can't answer that for you. And I actually am coming to understand that there's no one right healthy diet for everyone. I think we all need to maybe stop paying attention to what's out here and really start focusing on what's in here and how we feel. So I have a few questions for you to ask yourself when you're thinking about, is this food healthy or not? How do you feel after you eat it? Right? Like, kind of a number one question. If you eat something and it makes you feel tired, brain foggy, gives you joint pain, makes you really cranky, makes you bloated, gives you a headache, like, it could be the broccoliest broccoli, and it could be terrible for you at this time in your life. So again, I would say if we spend less time listening to the chatter and more listening to our bodies, we can intuitively know a little bit better about what's good for us. Just some more questions. Would your great-grandmother look at whatever that food is and know that it's food? Because I don't know about you, but you go to the grocery store and there's plenty of food. I know all 4 of my great-grandmothers would be like, I don't know what that is. So, and it's not to say never treat yourself or never eat anything that isn't, completely a whole food, but just be aware, Can you find all the ingredients on the label in the store? Can you look at that label and go, okay, that's in aisle 4, that's in aisle 5, that's in aisle 6, or would it only be found in a lab, right? Do you need a degree in chemistry to understand the label? So just questions to ask yourself to increase your awareness. So, all right, a little confession. Like, what I like to do for fun is go to the grocery store and look at labels. So I'm a very cheap date. So datum. Who's heard of datum? Yeah, I hadn't either. So I was, in preparation for this talk, I'm walking through the grocery store, taking picture of labels. I'm sure I looked completely obnoxious. And I'm like, what is datum? I keep seeing datum. Like, it kind of sounds like dates. Like, maybe it's fruit. What is this? So then I go home and I get on the computer. And that's what datum is. And I'm really impressed if anyone knows what that is or even how to say it. Would anyone like to give it a try to say that? Okay. Yeah. Well, it's bad when the easier to say name is capital E 472 lowercase e. Like, I don't know about you, but that doesn't make me feel much better about eating that. So, if you need a lab and you need a degree in chemistry, again, it isn't like never eat that or feel bad about yourself. It's just kind of be aware. Like, that may not be a food that you want in your daily diet. Maybe that's whatever even that is. It's actually a dough softener. So anyway, I did learn what it actually was. But just be aware, right? In general, and I don't care if you're vegan or vegetarian or carnivore or paleo or any in between, in general, lower sugar is better. Fewer ingredients are better. And this will be a little controversial, I get it. You may not have heard this before, but really try to avoid the processed seed oils. So while I know these are unsaturated, and probably, I don't know, grapeseed oil, is there a grapeseed? Whatever. If you got it right from the seed, it's probably fine. But I tell you, by the time these things are in the grocery store, in the bottle or in the food, they've been bleached and deodorized and processed in such a way that they're inflammatory. Okay, and so inflammation is what we really want to try to avoid. So even if the jug of canola oil says it's heart healthy because it's not saturated, that's an inflammatory food. So again, doesn't mean never have these things. It just means be aware, maybe minimize them, and don't always believe marketing. Cancer loves sugar. Cancer loves inflammation. Just thrives in an inflammatory environment. Your cells, your DNA, your mitochondria, it loves really simple, nourishing whole foods. So just kind of keep it simple, right? It doesn't have to be complicated. And I get that knowing what to do and knowing how to do it is entirely different. So I would invite all of you to a workshop that I'll be running in a couple of weeks. It's 6 sessions, and it's called Your Genes Are Not the Boss of You. Because just because we might, be a carrier of a high-risk gene, it doesn't mean that that has to dictate our life and our health. So this workshop is really aimed at people who know they want to make changes but are completely overwhelmed by the idea. It's really a foundations in health-related habit change workshop. So I would love it if you came. You're more than welcome to register. So you have 2 things now. So you have your homework assignment, which is the patient questionnaire. And then I also have some postcards, so thank you. So if you're interested, or you know someone who might be struggling a little bit with making habit changes, again, I am a health coach, I would be happy to help. I think it's part education, part support and community, and it's just easier to do hard things when we're doing them together. And, that's the joy and maybe hardship, I don't know, of being a human, is we need each other. In conclusion, far too many people will be diagnosed with cancer this year, far too many. And, we all have marbles in our jar. We all have a risk. We live in this world. We have different genetics, but we all share this environment. And yet we can all make choices, and we can support each other in making healthy lifestyle choices. We can understand our genetic vulnerabilities, and we can do something about it. We can make a plan. We're not a victim to our genes. So if you would like to talk genetics, I would be so happy to see you in the Cancer Center. You're more than welcome. You need to ask your doctor for a referral, but that's also where that questionnaire might be helpful. If you want to talk health-related habit change because you're maybe not so interested in chronic illness, or you want to help manage it a little bit better, I'm happy to talk to you in the context of my workshop or health coaching, just one-on-one, whatever works for you, because we all benefit from supporting each other. And I just feel really passionately that that's the way that humans work. We support each other. So that's my contact information. And if I can be valuable to you, please contact me. Thank you. Thanks. Oh, thank you. Thank you.